Okay, this is going to be a lesson about three-dimensional coordinate systems and vectors. We're going to begin with the distance formula, which says that the distance between 2 points P1 and P2 is the square root of the difference between the x-coordinate squared plus the difference between the y-coordinate squared plus the difference between the z-coordinate squared. And this just looks like an extension of the distance formula in 2 dimensions. It actually follows from the Pythagorean theorem. I'm going to zoom in on this diagram on the right here so that you can see that. If we look at the point x, y, 0, we can see that from the distance formula that the distance from that point to the origin is just the square root of x squared plus y squared. Now if we want to add the z-coordinate, then we can use the Pythagorean theorem to find the distance z. That distance is going to be the distance to the point x, y, 0 squared plus the z-coordinate squared. And we take the square root of that. And that gives us our three-dimensional distance formula, the square root of x squared plus y squared plus z squared. Now that's the distance to the origin. If we want to do the distance between 2 points, all we have to do is shift those points x, y, and z. I'm going to now do an example for you. The distance between the 2 points A and B is going to be the length of the line segment AB, which we denote with absolute value signs, and that's going to be equal to the square root of 1 minus 3 squared plus 2 minus a negative 2 squared plus 3 minus 5 squared. We can go ahead and simplify that. That is 2 squared plus 4 squared plus 2 squared. So that's the square root of 4 plus 16 plus 4, or the square root of 24. Now that we understand the distance formula for 3 dimensions, we can define the equation of a sphere. A sphere is really a collection of points that are all an equal distance from a centering point. That distance we're going to call the radius. So if we're looking for the distance from a point, say, x, y, z, to the center A, B, C, then the distance formula tells us that that would normally be the square root of x minus a squared plus y minus b squared plus z minus c squared. And then we would take a square root and set that equal to the radius, r. But instead of taking the square root, I will set x minus a squared plus y minus b squared plus z minus c squared equal to r squared. And that says that a sphere is every point x, y, and z that's an equal distance from the center ABC, and that equal distance is the radius r. Now that is an easy way to specify the equation of a sphere, but you might encounter an equation like this example that doesn't look the same as the format of the equation of a sphere that we had above, but does actually define a sphere. I'm going to rewrite that equation as x squared plus 4x, give myself some space, plus y squared plus 2y, give myself some more space, plus z squared minus 6z, and I'm going to set that all equal to the number 2. Now, in order to make this equation look like the one above, I'm going to complete the square for each one of the x, y, and z terms. So if I add the number 4, I'm going to use a different color here. So if I add the number 4 there, then that first expression is a square. If I add 1, then that second expression is a square. And if I add the number 9, that third expression is a square. Of course, I just can't add those numbers without adding them to the other side and making the equality true. I'm now going to factor each of the x, y, and z terms so that I get x plus 2 squared plus y plus 1 squared plus z minus 3 squared equals 16. So now we can see that our sphere has a center, -2, -1, 3, and a radius 4. When we talk about higher dimensional coordinate systems, we're going to use some notation. So sometimes you have seen the symbol R with an extra line there that represents the real numbers. When we talk about coordinates in the xy plane, we'll talk about R2. R2 is the set of all ordered pairs xy, where x and y are both real numbers. Now that we're moving to 3 dimensions, R3 will be the set of all ordered triples x, y, z, where x, y, and z are all in R. We can generalize this idea so that Rn is the set of all we call n tuples. These are coordinates x1, x2, all the way down to xn. And each of those numbers, x1, x2, down to xn, are all real numbers. And this brings us to the end of our overview of higher dimensional coordinate systems. You should read section 9.1 of the Stewart textbook in order to learn how to graph things in 3 dimensions and to fill in any gaps that are not at the beginning of this lesson. Now we really want to move on to vectors. A vector, we'll label that vector v, in Rn is an ordered set of real numbers that has the form v1, v2, all the way down to vn, and enclosed in those angle brackets. So the vector v is the collection of those numbers, and v1, v2, all the way down to vn are the components of that vector v. an example of a vector v in 2 dimensions would be the vector a, b. And we can symbolize that vector by looking at the point A, B, and then drawing an arrow that points to that point. And that would be the vector AB. In 3 dimensions, we may want to look at the vector A, B, C. And A is the distance in the x direction. B is the distance in the y direction. C is the distance in the z direction. And so to represent the point ABC, or the vector ABC, we would want to move in the x direction to the point A, then move. Okay, I'm sorry, I've made a mistake here. B is the distance in the y direction, and C is the distance in the z direction. So now if we want to represent that vector, we want to move in the x direction, a distance A, then move across a distance B in the y direction, and then up a distance C in the z direction, and then this small arrow here would point to the point ABC, and that would be the vector in 3 dimensions. Now we can talk about the length or magnitude of a vector, which is really the distance of that point to the origin. So the length of that vector is the square root of the sum of the squares of the components of that vector. So it's the square root of the sum of u1 squared plus u2 squared plus all the way to u sub n squared. And that is the distance of that is the distance of the point u1, u2, all the way down to un to the origin. Let's do 2 examples. So the length of 3, 5 is the distance of the point 3, 5 to the origin. So that would be the square root of 3 squared plus 5 squared, which is the square root of 9 plus 25, or 34. In 3 dimensions, the distance of the point 2, 1, 4 to the origin is the square root of 2 squared plus 1 squared plus 4 squared. So that is equal to the square root of 4 plus 1 plus 16, or the square root of 21. We will be finding the lengths of many vectors as part of this lesson and future lessons. I want to mention some properties of vectors. 2 vectors are equal if each of the components of those vectors are equal. So if we have a vector u1, u2 through un, and a vector v1, v2 through vn, then those 2 vectors are equal if u1 equals v1, u2 equals v2, and all the other components, pairs of components, are equal all the way down to un equaling vn. Now, the simplest way to define an addition for 2 vectors is to sum the components in the same positions. So the sum of the two vectors, u and v, is the vector whose first component is u1 plus v1. The second component is u2 plus v2. And the last component is un plus vn. Now we can picture the sum of two vectors in the plane or in 3 dimensions as follows. So I'm going to plot the vector u, which is the vector 2, 2. And then I'm going to plot the vector v, which is negative 1, 1. Now you'll notice that the sum of the two vectors, u plus v, is the vector 2 plus a negative 1 and 2 plus 1. So this the resulting vector is 1, 3. I'm now going to plot the vector 1, 3. That is this vector 1, 3. And from this, I can demonstrate to you the idea of adding two vectors, as they say, head to tail. So in order to add the two vectors, u and v, I would follow the vector u until I get to the endpoint. And then I would draw a new vector v parallel to the one that I've already drawn. And note that it would point exactly to the resulting vector 1, 3. Now, obviously, we would like u plus v to be the same as v plus u. So I could follow the vector v all the way till its end, and then draw a parallel vector to u, which also points to the vector 1, 3. So let's now look at the subtraction, which is the vector u minus v. The vector u minus v would be the vector 2, 2 minus the vector negative 1, 1. In the first component, that should be 2 minus a negative 1. And the second component, that would be 2 minus 1. The resulting vector is 3, 1. I will plot the vector 3, 1 on my coordinate system. And you will see that this vector lines up with taking the vector u, following it to its end, and then adding a negative or opposite direction of the vector v. You can also see that the resulting vector 1, 3 is parallel to the vector that connects the two heads of the vectors v and I'm going to put in a few labels that might have been missing. So the blue is the vector u, the red is the vector v, the orange is the vector u minus v, and the green is the vector u plus v. Okay, We're now going to move on to multiplication. It is unclear how you would multiply two vectors, although we will talk about this in the next lesson. But for now, we can talk about what is called scalar multiplication, or when you multiply a vector u by a real number, say c. When you multiply that vector u by that real number, what you do is you multiply each component by c. So c times u1, c times u2, all the way through c times u sub n. And then what that does is it increases the length of that vector by a factor c. If c is larger than 1, it may actually decrease the length of that vector if the magnitude of c is between 0 and 1. I'm going to draw a little picture of the vector u and then show you that 3 times u would be like adding 3 of the vector u to each other, and the result is 3 times as long as the vector u. Now that we understand scalar multiplication, we can talk about unit vectors. Unit vectors are vectors that have length 1. And unit vectors will be important all throughout multivariable calculus. So many times what we like to do is take a vector, say the vector a, and that vector has a length, maybe the magnitude of a, and we want to find a vector, a unit vector, that's in the same direction as that a points. The way that we do this is we take the vector a and we multiply it by 1 over the magnitude of a. The resulting new vector will have now length 1. You can see this. I'll make a little side computation here because the length of u, the unit vector, will now be the length of a divided by the length of a, which is 1. There are some important unit vectors in the plane R2 and in 3 space R3. So I want to talk about those. In R2, there are 2 important unit vectors, and we refer to them as I and j. I is a unit vector that points in the x direction, and j is a unit vector that points in the y direction. So the equation for I is 1, 0, and j is 0, 1. Your book will use bold type with I and j to refer to those vectors, but in physics many times they put a hat over the I and the j, as I've drawn for you, to represent that I and j are vectors. These unit vectors are important because they can be used to describe a point in 2 dimensions. So for example, if I look at the point AB, or the vector AB, then I can write AB as following in the x direction for a distance A, plus following in the y direction for a distance J. So you can see if I follow in the x direction or the I hat direction for a distance A, then that gives me the vector A I hat. And then I'm going to add to it the vector B J hat, which is a distance B in the y direction, or what we call the J hat direction. So now we've expressed the vector AB as the sum of two unit vectors, each scaled by a distance A and B. And so you need to get used to the idea that vectors will sometimes be expressed as coordinates, A, B, and sometimes they will be expressed using unit vectors, A I hat plus B J hat. Now in 3 dimensions, there are 3 important unit vectors in the x, y, and z directions. They are I hat, J hat, and now K hat. And I hat is 1, 0, 0. J hat is 0, 1, 0. And K hat is 0, 0, 1. So we can write a vector ABC as A I hat plus B J hat plus C K hat, saying that we will follow the x direction, or I, for a distance A, and then the y direction, or J, for a distance B, and the z direction, or K, for a distance C. Okay, I now want to do a couple examples finding you some unit vectors. So the vector 3, 5, we can find its length. The length of the vector 3, 5 is the square root of 3 squared plus 5 squared, which is the square root of 34. And now if we want a unit vector that's in the same direction, we would do 1 over the square root of 34 times the vector 3, 5. Or if you like, you can multiply in this 1 over square root of 34, and that's 3 over the square root of 34, 5 over the square root of 34. And you can verify for yourself that the length of this vector is 1. For the vector W, the length, again, is the square root of 2 squared plus 1 squared plus 4 squared, which is the square root of 21. And the unit vector in the same direction as W is 1 over the square root of 21 times the vector 2, 1, 4. Or we can write that as 2 over the square root of 21, 1 over the square root of 21, 4 over the square root of 21. And again, you can verify that the length of that vector is 1 by using the distance formula or the formula for the magnitude of a vector. Okay, now I want to talk a little bit about ways that we can look at vectors in the plane. So I'm going to draw a vector. I'm going to draw the vector AB. And I want to be able to describe that vector not just by its distance A in the x direction and B in the y direction, but maybe possibly as an angle from the origin, or an angle from the x-axis. I'll go ahead and label these axes. So I want to describe them as an angle from the x-axis and maybe a distance r. Now that distance r should be easy to figure out using the Pythagorean theorem, the distance formula, or just the formula for the magnitude of the vector AB. We see that that distance is the square root of a squared plus b squared. Theta, on the other hand, should be the arctangent of the opposite coordinate, which in this case is the distance b, over the adjacent distance, which is the distance a. And so this gives us a way to describe vectors in the plane, because as a distance from the origin, or a length of the vector, and an angle that gives you the direction of that vector. Now it's important to be able to start with a description in r and theta and get back to the coordinates x and y. So you should notice that A is, actually, let me tell you, you should notice that the cosine of that angle theta should be the adjacent distance A divided by the hypotenuse r, and that the sine of that angle should be the opposite distance B over the hypotenuse r. And so we can get the x coordinate A back as A being r cosine theta, and we can get the y distance back B as being r sine theta. And so you should be familiar with changing from the xy picture to the r, which is the distance from the origin, and theta, which is the angle from the x-axis, or changing from a description of a distance and an angle back to the x and y coordinates. So I will fill in the distances here, A, which is equal to r cosine theta, and B, which is r sine theta. Now we're going to put these ideas to good use by looking at an example from physics that involves vectors. So the example is that there is a 100-pound weight that is suspended from the ceiling by the means of two perpendicular flexible cables of equal length. So you can see the two cables hanging from the ceiling, but they make a perpendicular or 90-degree angle right there at the weight. And what we want to do is we want to find how much tension or force in pounds that there is in each cable. So in order to do this, I'm going to draw what in physics they would call a force diagram. So at this point, the weight has gravity pulling down on it. So that force due to gravity is going to be 100 pounds. And then on the right side, there's a cable pulling with a tension T2. And on the left side, there is a cable pulling with a tension T1. Now I'm going to draw a little coordinate system on here so that you can see what the angles are. I'm going to zoom in on this diagram so that we can see what's going on. So there's a 90-degree angle between T1 and T2. So we're going to assume that T1 and T2 are both at the same angle. So what's left is a 45-degree angle, or pi over 4 angle on the right side, and a 45-degree angle, or a pi over 4 on the left side. Now, because this weight is suspended from the ceiling and it is not moving, then the sum of all the forces, so the sum of all the forces must equal mass times acceleration, but that acceleration is 0, so the sum of all the forces, which are vectors, is equal to 0. So what we want to do is write out an equation that balances these forces. So what we're saying is that T1 plus T2 plus the force due to gravity has to equal mass times acceleration, which, because this object is not moving, is 0. What we're going to do is we're going to look at the x picture, the x component for these vectors, and the y component for these vectors separately in order to figure out the amount of tension T1 and T2. So for the x direction, the x component of T1 is going to be T1 times the cosine of the angle, which we will say is 135 degrees, plus T2 times the cosine of 45 degrees, plus the amount of the force due to gravity in the x direction, which we can clearly see is 0. I'm going to set that all equal to 0. So now the cosine of 135 degrees is going to be 1 over the square root of 2. Actually, that's going to be a negative 1 over the square root of 2. And then the cosine of 45 degrees is 1 over square root of 2. We're going to add those two up, set it equal to 0. And that's going to tell us that the tensions T1 and T2, which are the lengths of the vectors T1 and T2, both have to be equal. So I'm going to call these T. So this should be expected, because if we're balancing that cable, or that weight on these two cables, and the cables are both pointing in kind of equal and opposite directions at a 90-degree angle, we'd expect that the tensions in each of the two cables would be equal. So now let's move on to the y coordinate. the y-coordinate, we would see that we would have t1 times the sine of 135 degrees plus t2 times the sine of 45 degrees minus the 100-pound force, which is all in the y direction. And we would set that equal to 0. Okay, so the sine of 135 degrees is 1 over square root of 2. And the sine of 45 degrees is 1 over square root of 2. And we're going to move the 100 over to the other side. I'm going to remember that T1 and T2 are the same here. So I'm going to get rid of the T1 and the T2. So we see that T times 2 over square root of 2 equals 100. So T must be 50 times the square root of 2. And so what's interesting is that in order to hold this 100-pound weight, the tension in each of these two cables, because they're at an angle, is not 50 in each direction, but 50 times the square root of 2. And this is a good example from physics about how to work with the descriptions of two vectors given by their magnitude, T1 and T2, and their angles from the x-axis, which were 45 degrees and 135 degrees, and break them up into their x and y components so that we could decide how much of T1 and T2 as vectors were in the x and y direction. Okay, that concludes this lesson, and you should now be able to do the homework from sections 9.1 and 9.